All right. I'd like to welcome everybody to this issue of Gauge Theory Virtual. You can unmute and ask Laura questions if you have them. Of course, next week we won't have a meeting since it's Thanksgiving, but we will have a meeting the following week. We're delighted to have Laura Fredrickson speak about the asymptotic geometry of the Hitchin moduli space.
Yeah, thank you for the invitation. It's an honor to be here virtually today. So today I'd like to talk about an intricate conjectural description of the asymptotic geometry of the Hitchin moduli space coming out of physics. And I'd like to also talk about our efforts and progress to prove aspects of this conjecture using the tools of geometric analysis. All right. So, and feel free to interrupt me on any of this stuff. But we begin with the Hitchin moduli space. And so to define the Hitchin moduli space, we'll fix C to be a compact Riemann surface. There's generalizations where we can include punctures, but I'll start with no punctures to kind of generally. And then we'll pick a Lie group, SUN, or its complexification, and that will be give you the rank of the bundle. So we'll fix a complex vector bundle of rank n over C, and we'll fix, we'll only let the automorphisms of E, we'll only consider automorphisms which fix the determinant of E. So I'm writing, we have SLE automorphisms. So from this fixed data, we get a Hitchin moduli space. And this will be the moduli space of some equations, and I'll define that too. But first, the Hitchin moduli space, it really has a very rich geometric structure. And this particular one, the Hitchin moduli space is hyperkaler. So there's some nice interpretations of this hyperkaler structure. That means that there's a single metric and a whole CP1 family of complex structures. And so that means that actually you have a CP1 family of Kaler manifolds, and you can actually view each of these Kaler manifolds as an avatar of the, each of these Kaler manifolds can be viewed as the moduli space of some less restrictive equations. So the Hitchin moduli space is this is hyperkaler and is very restrictive, and each of these kind of CP1 family of avatars is the moduli space of less restrictive equations. So if we fix zeta to be 0, we'll get the Higgs bundle moduli space. If we fix zeta to be in C star, this will be the moduli space of flat GC connections. So you can already see with this moduli space of flat GC connections that the Hitchin moduli space is connected to representation theory of surface groups, and is a source of some interest. Let's see. Okay. So I'll start, I'll take a Higgsy perspective. So I'll be kind of focusing on the zeta equals 0 complex structure because it is distinguished. So a Higgs bundle then, so is a pair consisting of a holomorphic structure on E and a Higgs field. And so the Higgs field is a 1-0 form valued in the traceless endomorphisms. But we can do this all locally. And so on some local patch, we can pick a trivialization such that del bar of E is just del bar. And then the Higgs field, what it's going to look like is some trace-free n by n matrix that has holomorphic entries. If Z is some local coordinate on C. So that's what we have. And so then we can talk about the Higgs bundle moduli space. And there's some kind of simple cases. If we just do GL1, we're just considering line bundles over the curve C. And so, so supposing we're considering degree 0 line bundles, then we naturally, the holomorphic structures is just a Jacobian on C. And then the Higgs field, what this needs to be it needs to be a section then just of the 1-0 forms, holomorphic 1-0 forms. So it's a holomorphic section of the holomorphic cotangent bundle. And then the things become even simpler. For example, if C is just the 2 torus with complex modulus tau, then you can just identify the Jacobian of the torus with itself. And then the holomorphic cotangent bundle is just going to be, you're just looking at bounded holomorphic functions you can unfold the torus because it's just a lattice to, you can view the torus as just a quotient of C mod a lattice, and then a Higgs field is just a bounded holomorphic function on C, and so that means it has to be a constant. Sorry about that. And so then the moduli space is just this torus across C. So I included this because what you see in this, even this easiest example, is some very central stuff. Oh, by the way, you can't see my Zoom stuff, right? You can't see the Zoom group chat or anything, can you?
Yes, we do see it.
Oh, right.
It's good now.
You don't see yourselves though, right?
No.
Good. Okay. That's pretty annoying. Yeah, so that in its avatar is that you always have this structure that a Higgs bundle moduli space is an algebraic, completely integrable system. So what that means is that you have this fibration. M is a holomorphic symplectic space, and it's fibred over a half-dimensional complex space. This map is easy to describe. You're sending this Higgs bundle to just the collection of eigenvalues of the Higgs field. So because the Higgs field is locally an n by n matrix, there's n eigenvalues, and so that's what the point of the base is encoding. Yeah, and so also these all the fibers of this map from M to B are Lagrangian, and the generic fibers are compact abelian varieties. But this would be pretty simple, as it was in this kind of case of the torus, if they were all abelian varieties. So there's the most interesting stuff is happening by the singular locus, which I've drawn in red. Now this is a complex codimension 1 locus where the fibers are not abelian varieties. So what you can see is that this picture is a bit of a lie, because the red stuff should be complex codimension 1 in the base. So real codimension 2, but I drew it this way because, so for a complex one-dimensional base, you would have just the singular locus would be some discrete set of points. But when you go to higher dimensions, you can have these singular loci, which go out as rays to infinity. And that's where the asymptotic geometry is most interesting, is near these singular fibers that are going out on rays to infinity. So questions so far? Okay.
So what did you say the base of this was? This is not the determinant map, or is it?
Yeah, it is the so you're right, for SL2 would be the determinant map. Because if you want to keep track of the eigenvalues lambda and negative lambda, that's the same as just computing the determinant of your matrix, so lambda squared. But in higher dimensions, it basically is just a map from the Higgs field to the characteristic polynomial of the Higgs field.
So is just to understand in this case, is the singular fibers are happening where the two eigenvalues come together? Or is it some other phenomenon that's?
Yeah, so it's when two eigenvalues are coming together, but in so they can come together in a simple way.
Mm-hmm.
But yeah, if they're coming together in a non-transverse way, that's exactly what's happening. Yeah.
Thanks.
Yep. Okay. And so then Hitchin's equations, which are the souped up version for the whole hyperkaler on moduli space. These are equations for then a Hermitian metric on E. So you can start with the Higgs bundle, and then Hitchin's equations become equations for Hermitian metric on E. And so this equation is that the curvature, that's the F of the Chern connection, so associated to del bar E and H. So the unique H bar unitary connection, whose 0, 1 part is del bar. And then there's this kind of perpendicular sign, so that the trace-free part of the curvature of the Chern connection plus the bracket of phi with its H Hermitian adjoint, so is equal to 0. And these are Hitchin's equations. And these are a coupled system of n squared nonlinear elliptic PDE. It's second order in H, and you can view, if you want, f of d, this curvature, as some sort of Laplacian-like term, like Laplacian of log H. That would be what it would be in the rank 1 case. So so that's what you've got, and because these are coupled and nonlinear, it's not reasonable to expect that you could solve the Hermitian metric for the Hermitian metric, or kind of get access to this. So there's a correspondence between stable Higgs bundles and solutions of Hitchin's equations. So that means that anytime you have a stable Higgs bundle, the algebraic condition of stability guarantees the existence of this Hermitian metric H, solving Hitchin's equations. And so you can view this solution of Hitchin's equations as an upgrade of a stable bundle. And so you have these two moduli spaces, but you'll see that the gauge groups change, because on the right, I want to preserve the Hermitian metric, and on the left, we don't need to preserve the metric. All right. So there's this conjecture by physicists Gaiotto-Moore-Neitzke, and I'll mostly skip this, but where it's, so the Hitchin moduli space, if you want, you can introduce a parameter t. This is kind of maybe a bit of a silly thing to do, but you just put this parameter t squared in front of the bracket of the Higgs field with its adjoint. And these Hitchin moduli spaces, they arise as moduli spaces of certain supersymmetric field theories, compactified on a circle of radius t. So there's this BPS spectrum, something that you can compute from your field theory. And their claim is, their conjecture is that the VPS spectrum can be recovered actually from the asymptotic geometry, or the geometry of the family of this MT as t is going to 0, or t is going to infinity. So what does this what's happening to this family of Hitchin moduli spaces? Well, the length scale of these Lagrangian fibers is 1 over t, so these are crushing down. It's kind of similar into as you're approaching a boundary of the K3 moduli space, so you have some crunching going on. There's a natural semi-flat metric, which is just coming from the integrable system structure on each. And so roughly they're saying something like this, that the difference of these two metrics is some sum over all of the loops in the first homology of some space, which I'll describe in a minute. And then you have some integers here, these omegas, these, and then you have something exponentially decaying, e to the negative LT. So these integers, these are these omegas, these are these BPS indices, and these are piecewise defined on the Hitchin base. So if you fix gamma, and then you can view these as piecewise constant functions on your Hitchin base, and then these jumps are constrained to satisfy some Kontsevich-Soibelman wall crossing. And so that's just kind of the shape of the conjecture. And they give also a recipe that if you have some integrable system data and some BPS indices, then you can go backwards and you can construct hyperkaler metrics. So that's the conjecture in general, but there's many of these Hitchin moduli spaces admit C star actions, where you just basically are rescaling the Higgs field. And then you can see that actually rescaling the Higgs field by T is really the same thing as putting the parameter t in front of here. And so you can turn this into a conjecture about a single Hitchin moduli space, where what instead you do is you fix a single Higgs bundle, and then you look at all rescalings going out to infinity. So you rescale it by t, and then look at this this ray in the Hitchin moduli space, and then the metrics ht, solving the t rescaled Hitchin equations, and so you can actually kind of the claim is that you can recover the BPS indices of this theory from the asymptotic geometry of this single Hitchin moduli space. Okay, questions? All right, so the simplest form of the conjecture would look something like this. That you have these two metrics on two hyperkaler metrics on the Hitchin moduli space. One is this GL2. It's called an L2 metric because it just looks like norm of the Higgs field squared plus norm of this basically the deformation of the flat connection. So the deformation of the holomorphic structure squared. It's something like that. And so to get access to this hyperkaler metric, you really actually need to understand the Hermitian metric solving Hitchin's equations at every single point of your moduli space. So this one is very sensitive, and you really need to consider this coupled system of nonlinear PDE to get access to that. But then there's a much easier metric called the semi-flat metric. And this is flat on the torus fibers. That's why it's called semi-flat. And it's not flat on the base. And this comes just directly from the integral system structure. So this was defined in the work of Dan Fried. And in some sense, this metric is singular as you approach any of the singular fibers. And in some sense, that's because it's far too symmetric. Because it's flat on the torus fibers, you can see something kind of is developing here when you have something pinching off. So this semi-flat metric is just too symmetric to extend across the singular locus. So then the conjecture is that the difference of these two metrics, as long as you stay away from the torus, these singular torus fibers, is exponentially decaying in t, and the Gaiotto-Moore-Neitzke give the, if we just are considering the first correction, they give both the constant in front and the rate of exponential decay. And so this is the first form of the conjecture that I'll turn to. And I'll summarize kind of the results in this direction to start before talking about the strategies. So in 2017, Rafe Mazzeo, Jan Swoboda, Hartmut Weiss, and Frederick Witt, they proved that the difference of these two metrics was polynomially decaying if you considered the SU2 Hitchin moduli space. So then Dumas and Neitzke, David Dumas and Andy Neitzke, they proved that you had exponential decay. Not if you considered the whole SU2 Hitchin moduli space, but this one Hitchin section. This is the section that's most directly related to Teichmuller theory. And in this Hitchin section, Hitchin's equations go from being a coupled system of PDEs to a single nonlinear PDE. So this is really much easier. And then since then, I proved exponential decay for the SUN Hitchin moduli space. And then with Rafe Mazzeo, Jan Swoboda, and Hartmut Weiss, we also proved exponential decay. If you introduce, you allow your Higgs field to have simple poles along some divisor of C, which is the case of these parabolic Hitchin moduli spaces. So what I wanted to talk about in the rest of this talk is kind of this question about the interplay of math and physics, and how geometric analysis gives you insight into the physics conjectures, and then how these conjectures in physics also stretch the limits of geometric analysis and kind of raise some problems to get around. And so I wanted to just describe a little bit about what we've done and kind of what the difficulties were. And then lastly, I wanted to specialize to the four-dimensional Hitchin moduli spaces. So Hitchin moduli spaces are hyperkaler. So you have the zero-dimensional Hitchin moduli spaces, which are maybe not that interesting geometrically. And then the smallest ones then are these 40 Hitchin moduli spaces. And you can only get these if you introduce punctures on your curve C. And the reason why I wanted to talk about these is that actually 4D non-compact hyperkaler spaces are well studied since the work of Kromheimer classifying ALE gravitational instantons. And there's a whole other community working on all this stuff. And so I wanted to describe our progress for one of these types of 4D Hitchin moduli spaces and how these Hitchin moduli spaces then fit into the classification of 4D non-compact hyperkaler spaces. And then one other thing that this going to the 4D case lets us do is to try to get the optimal rate of exponential decay. So as I mentioned, kind of in these last three results, the rate of decay is not optimal in any of these. But when we go to the simplest case, we're actually able to get the optimal rate of exponential decay. And I can
is there some, when you say optimal, is there some sort of guess in advance as to what that, you're talking about the L, the quantity L?
Yeah. So they give a formula for it. It's some integral of the tautological one form.
Okay. So
over
nothing,
some,
that we're going to make sense of, I guess.
I can actually make reasonable sense of it. Yeah.
No, but no, you can. I'm not saying, maybe I can't.
Yeah, but this is a number that they compute. Yeah. Okay. So unfortunately, I would like to tell you what L was more concretely. Actually, I can kind of do it in this picture. So L is going to be the integral. You have all these kind of loops in this. Oh, let me get to that in a minute. All right, so table that. What is L? So this is the conjecture, is that if you fix a Higgs bundle in the regular locus away from the singular fibers, and then you can fix a Higgs bundle variation, which I'll denote this way, eta dot and phi dot, then if you go along this ray going out into the Hitchin to the ends, and you measure these two deformations with respect to the L2 metric and the semi-flat metric, that the difference of these is exponentially decaying in T. So that's what we proved. And so I want to tell you kind of where this is the hardest and how this works. And it starts maybe by trying to understand the behavior of this metric, this family of Hermitian metrics, HT on E as T goes to infinity. So what you have is a very traditional kind of bubbling phenomenon. That what's happening is that this curvature is concentrating as T goes to infinity along this branch divisor Z. So what Z is so the Hitchin moduli, the Higgs bundle is at each point it's a 5x5 matrix, and so this is if it's SL5, so it's some n by n matrix, and so this is the 5 case, and so it then has generically n eigenvalues, and when these eigenvalues collide, then you're going to get a complex codimension one, so you're going to get locus, so some points in your curve Z, and this is where you're having concentration of the curvature. So then in fact, the curvature is not only concentrating there, but it's everywhere else it's going to 0. So usual bubbling phenomenon, you're leaving behind a very simple limiting metric, H infinity, and then at each of these points you've bubbled off some sort of instanton, which we can describe. And so that's what this HT is looking like. So then because of that, the main difficulty is really going to be dealing with contributions. So all of these L2 metrics and the semi-flat metrics are some sort of integral over C of some stuff. And you can see that this limiting metric is going to be flat with singularities along Z. And so really all the difficulty is going to be coming from really these infinitesimal neighborhoods, because that's where things are singular, and everywhere else things are pretty simple. So lastly, what is this this L? So there, this spectral curve, which is this ramified end-to-one cover of C, just consisting of the eigenvalues. Well, because the Higgs field looks like some matrix times dz, it's naturally living in the holomorphic cotangent bundle. And so the holomorphic cotangent bundle has it has that tautological one form, and you can integrate that then over any homology cycle, any H1 in this spectral curve. And so I could integrate over this little square or this little thing right here. And what L is, so what's happening as you're going to singular fibers is one of these homology cycles is crunching down to 0. If you're in the determinant, the rank 2 case, and you only had a 2-to-1 fiber, basically you could be looking at the determinant of the Higgs field, and you're starting to move 2 simple zeros in your determinant together to form a double zero, and that's kind of what it looks like. And so that is what this L is it's the minimum integral over all of these homology cycles. Okay, so there's a couple ideas in the proof, and the first one is, I'll just write down the L2 metric. Can't avoid it forever, though we can try. As you kind of consider a Higgs bundle variation, eta dot and phi dot, you can also actually phrase this in terms of a metric deformation. Nu dot of t of h of t, and then the L2 metric can be written in this way as the sum squared of these two deformations with respect to ht. And what this metric variation is it's actually a unique solution of this equation here. Okay, so the first thing is that this the semi-flat metric, which is defined from the interval system structure, it doesn't really come to you when it presents itself as an L2 metric, but you can actually realize it and show it's the same as the L2 metric above, but defined using h infinity instead. So if I just replace everywhere you see a nu dot t, replace that with nu dot infinity, and everywhere you see an h of t, replace that with h infinity, then the semi-flat metric is actually the same thing. The only difference is that the metric actually, this equation splits, and nu dot infinity solves these two decoupled equations. And so that's the first thing to put L infinity, the semi-flat metric, on the same kind of analytic footing as L2. All right, so the next kind of idea in all this stuff is kind of, is just that this is a bubbling phenomenon. So we're going to build some approximate solutions of HT to understand it better. And the way we're going to do that is that we have this simple thing that's left behind after bubbling, which is H infinity. And I've drawn that here, singular at Z, that's the little orange spikes. And so the reason why it looks like a delta function is because the curvature has some delta function singularities at H infinity. But what we're going to glue in then is some solutions. We have kind of model solutions on any neighborhood, and we can glue those in as a way of desingularizing things. So to make this concrete, what you see is that if we're in the rank 2 case, you claim you have the determinant. You see that the eigenvalues here are plus or minus square root of z. And so they collide at z equals 0. And then I can actually, H infinity, what it is it's this singular metric here. And I can come up with some model solutions, HT model, where U has kind of a bad logarithmic singularity at z equals 0, which is going to precisely cancel out kind of this singularity type here. So these are these models. And then if I want to build an approximate solution, I just introduce a cutoff function going from 1 kind of inside the disks to 0 outside the disks. And it solves Hitchin's equations everywhere except for on these light blue annuli. where the cutoff function is in the open interval between 0 and 1. So, this is a way to build an approximate solution. The question is whether it is a good approximate solution. And indeed, it's a really good approximate solution. And this is because that function before u of t appearing here is really exponentially decaying and very quickly. And so that the approximate, this ht approximate, this approximate Hermitian metric differs from the true Hermitian metric by exponentially decaying orders, exponentially decaying errors as t goes to infinity. Unfortunately, you have a family of family of operators LT, which are degenerating and have something singular, and so the difficulty is showing that the first eigenvalue of some operator is bounded above by something. So this is an analytic result. So what the approximate solutions let you do is actually, you could define a non-hyperkaler L2 metric G approximate by doing the same kind of silly thing. Everywhere you see now a nu dot of t, replace it with nu dot approximate. And everywhere you see an h of t, replace it with ht approximate. And then if you want to study the difference of these two, GL2 and GSF, you can actually break it into these two pieces. The L2, the approximate metric, the L2 minus the approximate metric, and the approximate minus the semi-flat. And it's a corollary that because the HT and the H2 approximate are exponentially, the order is, the error is exponentially decaying as t goes to infinity, that this first term is also exponentially decaying in t. And so really the only all the problem, again, like I said, it's always localizing on these, around this divisor where your eigenvalues are crossing. And so then the last thing is to deal with G approximate minus G semi-flat. Okay, so so if you remember how we built a HT approximate, HT approximate was actually equal to H infinity, kind of outside of these disks. And this implies actually that G approximate minus GSF localizes up to some exponentially decaying errors to actually these disks where they differ around the points. And so this is exactly, some more localization. And so now we've everything is reduced to understanding the behavior of these disks. But these disks, just understanding the difference of these two metrics on the disks is still not a trivial thing. So Matteo, Somoda, Weiss, and Witt had done all of this, and they still got polynomial decay, and that was from these disks. And the problem then is actually there's infinitesimal variations of the Higgs field in which the branch points move. So let me go back a couple pages. So you see these these little on the blue dots with these orange arrows back to here. So you could consider Higgs bundle variations. And as you move your Higgs bundle variations, all the eigenvalues are going to move. And actually then these eigenvalue crossings could move. And this is precisely what is the worst situation. And so if you just include those and do the, the reasonable thing that you get, there's possible polynomial terms, but Gaiotto-Moore-Neitzke, they found a nice trick for dealing with this. And what they used is they used a family of biholomorphic maps on these local disks. So they had some little infinitesimal flow, holomorphic flow that they introduced on these disks that was perfectly matching the changing location of these branch points. And the reason why this works fundamentally is because Hitchin's equations are conformal. And so they're able to pull back by this, and then basically to get rid of this infinitesimal movement of the disks. And so with that, they get you can get exponential decay even of the G approximate minus GSF. And so, yeah, so that is really kind of the three, I'd say, main ideas behind the theorem. And so with that, any questions? We can turn then to these 4D cases.
Do you have a good model for what happens when, I mean, do you have some good model solution for the case that some of these zeros approach each other, they collide with each other?
Yeah. So I wrote about this in a paper with Andy Netzke, and yeah. So right. So what kind of order are you considering?
I mean, when there are multiple roots.
Oh, multiple roots.
Yeah.
Okay, so that gets a lot harder. So right, the reason for staying kind of away from in the regular locus is that basically there's a unique model to glue in. There's a unique bubbling model. But once you start to allow, so when you have these multiple roots, so basically now your eigenvalues aren't intersecting transversely. They're intersecting kind of with a multiple root. Are you thinking multiple roots that way? Are you thinking like SLN, or are you thinking kind of like determinant hierarchy?
Even in the case of SU2, when your quadratic form has multiple roots, my understanding is that, I mean, it's hard. That's the hardest part of understanding the end of Hitchin moduli space, right?
Yeah, no, yeah, that's completely right. Yeah, so right, and then you have to go to moduli spaces. And so you hope, I think the way that would go, so we haven't done that. We've considered doing it maybe on the Hitchin section. But yeah, is that there should be some way of matching up. So you have moduli spaces of kind of model solutions of these, what's bubbling off. You can kind of keep track of some sort of kind of some data, some like the representation theory of these bubbling solutions. So you should know kind of which ones to glue back in. But then the gluing theorem just gets a lot harder because you're picking things out of these really much bigger moduli spaces of model solutions. And so yeah, I described some of these like in the paper with Andy, like somehow it's much easier to do not the double zero case, like if you're in SU2, but the triple zero case in your determinant. So like having it be coprime is much easier than having it not be coprime. But yeah, for these, you get to these wild Hitchin moduli spaces.
I see. All right. Thank you.
Okay. So yeah, so here we have the two results. You could see how well did we do. I'd say reasonably well. We got exponential decay. Unfortunately, the rate of decay is not optimal. So this L is what they predict, and what we can kind of get is L over 2 minus delta for delta arbitrarily small. And this is because L in some sense is related to the distance between the two, the nearest points in the divisor. And if we're going to be doing these balls around each, we've kind of implicitly kind of cut that distance in two. So we're only getting half the decay that we should from this kind of gluing construction. And so you also see that they also conjecture something about this coefficient, and we have nothing like that. So both some success and also, some certain areas for improvement. And so then I want to describe in these 40 cases, both because it's a beautiful picture of the classification of non-compact hyperkaler four-manifolds. And then also because we can maybe get some better decay. Okay, so all right, so the theory of non-compact complete connected hyperkaler four-manifolds of real, these are also known as gravitational instantons, sometimes, is a classical subject. And so I wanted to briefly review it and ask the question of how 4D Hitchin moduli spaces fit in. Skipping kind of this first step and starting at ALE. Kronheimer, he classified all of the hyperkaler, all these gravitational instantons such that the volume growth of balls of radius r is asymptotically like r to the fourth, and he found that these are asymptotic to some standard model. You'll notice this is singular, which is C2 mod some finite subgroup of SU2. And so these are all smoothings of that. So more recently, Chen and Chen proved that if you insist that the Riemannian curvature tensor decays faster than quadratically, then actually you necessarily get that the volume growth of these balls has to be either r to the fourth, r cubed, r squared, or r to the first. So you can't have weird things like r to the four-thirds. Or anything else between that. So Minerb proved that there's no gravitational instantons with growth between r cubed and r to the fourth, but it's unknown sort of whether there's other gravitational instantons without this curvature decay that kind of live in between here. And actually, Hein has constructed some gravitational instantons that have volume growth like r to the four-thirds, but they won't have this faster than quadratic curvature decay. So there's a whole big zoo here. So if you were a betting person, you might guess that the Hitchin moduli spaces would fit into this ALG thing, because we've seen this this Hitchin vibration of this this torus over the base, and that's really looking kind of like volume growth like r squared. And so then there's a classification then, sorry, this is just two Chens, classified ALG and ALH spaces. And the classification of ALG is that basically it's asymptotic to some standard model of some cone of angle 2 pi beta here, where beta is between 0 and 1. And then you have just some sort of constant torus vibration with T2 tau asymptotically. So these are your models. There's these kind of two more recently described kind of non-classical families, ALG star. They have volume growth like r squared, but they have kind of slightly slower, not quite the curvature decay that you want. And then there's these weirder ones, ALH star, that have the right curvature decay, but sorry, they don't have quite, they're right at r to the -2, so not r to the -2 plus epsilon. And they have this volume growth like r to the four-thirds. So all of these examples, ALG, ALG star, and ALH, are all given by rational elliptic surfaces, which is kind of like the Hitchin, so the Hitchin moduli space, because of this complex, this holomorphic symplectic structure has that. And so you could ask, where do the 4D Hitchin moduli spaces fit into the classification of gravitational instantons? So, there's this modularity conjecture posed by Philip Boalch, which says that every 4D Hitchin moduli space is of type ALG or ALG star, so it definitely has volume growth like r squared. Conversely, and this is maybe more surprising, that every ALG and every ALG star, so all of these ALG things can be actually realized as the hyperkaler metric on a Hitchin moduli space. So if you want to exhaust all the ALG things, you can just look only at Hitchin moduli spaces. And so you can come up with a nice chart if you wanted of the various values of the cone angle and the parameter of tau, and sort of what should be the Hitchin moduli spaces you should take, what should be the base curves, what should be the divisors, and what should be the rank of the bundle. Of course, what you start to see is that you might need to introduce wild Hitchin moduli spaces. So these are places where the Higgs field has higher than a simple pole at some point. And in these last ones, you have an irregular singularity, so a non-simple pole at this infinity. But yeah, so this would be kind of the full version of this conjecture. And so what I want to specialize then is to this case of the I0 star ones, because this is somehow the easiest. So this one is just trivial. Unfortunately, I already described this one at the beginning, what all the Hitchin moduli spaces are. There's a single one. But for this one, we actually have maybe, we have a 12 parameter family of ALG spaces and a 12 parameter family of Hitchin moduli spaces. And so the hope would be to show that these are actually coincide and line up. And also in this example, I can show more explicitly sort of what this semi-flat metric is, what just GL2 is, and what this G model is, and how they all differ. So there's a 12 parameter family of SU2 Hitchin moduli spaces on CP1 minus 4 points. Things get a little more complicated when you introduce these divisors, because you have to fix 2 extra pieces of data. You need to fix something called the complex mass, which is the eigenvalue of the residue of the Higgs field. So the Higgs field now is a simple pole, and so you can talk about its residue. And then you also need to fix some real mass, these parabolic weights, because now your Higgs bundle is not just a regular holomorphic bundle, but it's a parabolic bundle. So it has some flag structure and some parabolic weights. But kind of analytically, this is being encoded. This is encoding the blow up that the Hermitian metric has singularities like z to the 2 alpha p as you go to the divisor. So with these, 1 complex and 1 real at each of the 4 points, so that's a 12 real parameter family, you get a Hitchin moduli space. And in this case, we can see really explicitly what it should be asymptotic to. This cone angle down here is just pi. This torus is basically the elliptic modular lambda function of P naught. And the volume of each of these fibers asymptotically is 4 pi squared. So, so generically, this fibration has 6 singular fibers. That's because these 6 singular fibers are the location of the zeros of a discriminant of a quartic, and the discriminant of a quartic is order 6. And so that's what maybe this generically would look like. They're all I1 fibers. And so then what you can see is that the semi-flat metric has some sort of logarithmic singularities. It should be modeled on the Roy-Baca, but we haven't shown that yet. Near these points, these singular points. And so the semi-flat metric is not the same thing as the model metric. However, what we'll see is that actually if you collapse and bring all these 6 singular fibers into one really big fiber at the origin, then it coincides. And so when you have only a single singular fiber rather than the 6, you call these spaces strongly parabolic, and this corresponds to turning, making all the complex masses 0. So we could prove all of these are ALG, and that we actually have Riemannian curvature decay of r to the -4th if all of these complex masses are non-zero. But if actually they're all 0, we actually do get exponential decay of the Riemannian curvature tensor. So there's some special space. And so with that, we'll turn to this strongly parabolic Hitchin moduli spaces. So this is a special 4-dimensional family in the 12-dimensional space, because we've set all the complex masses to 0, and all the things that we have at each point is in a real mass. And so now the semi-flat metric is the model metric, and it's much easier to talk about this conjecture. So then the question is it possible to prove Gaiotto-Moore-Neitzke's conjecture and get the optimal conjectured rate if we're considering just strongly parabolic things? And the answer is going to be yes. And one thing I want to emphasize while we're on this picture is that with strongly parabolic, you have a circle action. So you'll notice that this whole picture is symmetric around the origin. And that we have this one kind of bad, funky fiber here. And so this circle action is really invaluable. So the way that we can use this circle action is that Claude Lebrun, he gave a framework to describe all Ricci flat Kähler metrics of complex dimension 2. So this includes then hyperkaler manifolds, provided they have a holomorphic circle action in terms of two functions u and w. Now, because we're hyperkaler, we can actually even do better. We can do it in terms of a single function u. And so what we're going to do is we're going to consider the hyperkaler metric, and we can break the Hitchin base, this complex plane, into both the radial part and the angular part. And it's this angular part going around, because that's where we had the circle invariance. This will be the circle action. And then kind of we'll have this other put piece will be its own thing. So the hyperkaler metric on this thing can be written in terms of solely in terms of u. And then u on this torus in this radial direction solves this simple, it solves this single PDE. So, still on a three-dimensional space, so not great, but also not bad. And in this case, the semi-flat metric corresponds to just taking u semi-flat to be log r. And if you kind of just looked at this, you could see that that log r would solve this equation. So the real goal then is to show that u minus u semi-flat has the conjectured rate of exponential decay. And we can do that. And so this is just a typical bootstrapping argument. So on the left hand, you set up the linear side, and on the right hand side, you set up the quadratic side. And what you can kind of just keep doing is that anytime you the first observation is really that the first exponentially decaying function in the kernel decays like this certain rate. So as long as you kind of stay below this this rate, that if you have v with a certain rate of exponential decay, then you know the quadratic piece in v also decays twice as fast. But now you can kind of bootstrap and you can solve LV of f. So if f then has decay like e to the negative 2, then you can find that v has decay, that same decay up until this this first eigenvalue of the kernel. And so with that, we can get that the difference of these u minus uf is actually exponentially decaying with this parameter lambda t. And lo and behold, this is exactly the right exponential decay of Gaiotto-Moore-Neitzke's conjecture. And so this really actually gives an explanation for what L was in this case, is that it's the first eigenvalue of the torus, of the Laplacian on the torus with respect to the semi-flat metric. So, that feels a little bit better than some maybe integral of something. But we still don't have this first correction, omega of 8. So just to say, it's been a really fun set of conjectures to work on. Because it keeps kind of, it's just a nice challenge, and it keeps kind of pushing things farther. Yeah, and we really would like to get this 8 in the future. And then you'll notice, unfortunately, that I've only been talking about the first correction. And Gaiotto-Moore-Neitzke actually conjecture a really rich asymptotic, not an asymptotic series, just a series for this with all these different orders. So it's really rich. And yeah, thank you for your attention.